Good morning. So we didn't have quiz number 1, and actually I sent the solution and the video to explain the 3 problems there. So I just didn't have the problem and questions again, and in fact I want to make sure for the 3 problems, what's your status, what's your understanding. Well, so let me go through this quickly because I sent you the video and the solution. So just let you have the reference. This is the first one. We have the client server connected through N routers. And also we have the header length H bytes. And we have the size L. All right. 2 subproblems. The first one, we have a single packet. The second one, we have K packets. Well, and then we ask you to have the delay. So this is the first one. Well, then we have the solutions. Actually, I've checked the solution of your answers. And maybe some of you, or maybe most of you, use the description. In fact, if you want to have the results in detail, actually, you should have the diagram from client to server, the time diagram, and then you will have the solutions. You can try, and then, yes, it's true, we have the current solution. Similarly, we can have the solution to subproblem B. All right, so you can check the solution, and also you can check the video, or maybe right now I already have the hint. So about the solution to problem 1, think about this. And later I will ask you to have the understanding or comprehension checking. So this one, think about that. And second one, we have the propagation delay. And given a distance of the current one from the satellite to the surface of the Earth, and then we have the distance. Based on the distance, I ask you to have the propagation delay. And subproblem B asks you to have the current capacity multiplied the propagation delay. So just follow that one. However, I ask you to have the unit. So what's the unit for the second subproblem? And finally, the minimal length in bits. All right, and so that we have the continuous transmission. So I think this one, I ask some of you to have the exercise. Maybe not all of you, but at least we follow this one. First one, A, ratio B multiply C. Why? Because over 60, it's a minute. So this is a rate, and the rate equal to the transmission rate or the capacity. Then we have the solution. So this is the second one. And final one, actually, we consider the web caching. However, during the lecture, I ask you to have the calculation based on some assumption. Well, some assumption, a few milliseconds, microsecond, or something else. But right now, the current one is easy. We already have the assumption based on this. All right, we already have the assumption based on this. However, we have a delta. Delta actually is the average time required to send an object over the access link. So that says it's the transmission delay. And beta is the arrival rate of objects. So I think we have the assumption using the formula so that you have the delay calculation. And of course, we have the other delay for 4 seconds as well. And right now, we have two sub-problems. For the current one, we don't have the web cache. The second one, we have the web cache with the hit rate of a half. Well, then we have the calculation. And I know maybe some of you failed to have the final answer, but I still let you have the partial points. All right. And this is the solution to the third problem. Well, I go through quickly, and in fact, you can refer to the video of last year, and so that you can have the solution as well. So let me go to the check-in directly. That I have a few minutes to think about this, 2 minutes, because we have poll everywhere. So regarding quiz number 1 and the solutions here, I want to make sure your comprehension or understanding. So let me check this one. All right, go ahead and check it, 2 minutes. Think about this, or maybe 3 for you, because you need to think about this. We have 3 problems. So understood well. That says no question, no problems, and or maybe any place or points you think, okay, you need to ask me to re-explain. All right, go ahead. So let me make sure for students in the classroom, not finished. So let me go through the possible response from you. Some of you understood well. Good. So, one question, this one. Transmission delay in question 1 and 2, including propagation delay? Of course, no. Transmission delay is different from the propagation delay. And we assume zero propagation delay. So this is a question from Shaojie. And problem 3, sure, later I may go through problem 3. So, Fanya, you should have the answer, not the not the attendance checking. And Yujie, actually, no, the formula is important, but it's not the point of the current problem. We ask you to check the 3 problems. So that's all. Let me move on to the discussion for problem 3. So before I go, maybe let me make sure anyone still want to finish the answering? No, so let me get back to the solution to problem 3. Well, so this problem, the current problem is we consider a scenario. So we have the institutional network connected to the internet. So similarly, we have a LAN. And we have the access link. And we have internet. And here we have a 4 seconds. And as for the queuing delay, actually the queuing delay follows the current formula. And here we have a delta is the transmission delay. Actually, it's the transmission delay. And the beta is the arrival rate of the objects to the access link. Sorry, 4 actually should be this. Sorry, move it to this one. And this is a queuing delay of the access link. So we have a delta over 1 minus beta multiplied delta. It's the queuing delay. Here we call the access delay, so it's the access link. And 4 actually through the access link, then we need to take 4 seconds on average. Well, so something like that one. So we should have 4 plus the current delta over 1 minus beta multiplied delta, possibly. Why possibly? If we consider caching, then we have a different formula using the expected value. So this is the point for the general description for subproblem A. And subproblem B, we have a hit rate of 0.5. So look at this. First of all, transmission delay, is it true? Here, yes, transmission delay. Right? So let me check the students in the classroom about the current calculation transmission delay. Is it okay? Transmission delay. So transmission delay, is it true? here, length. And here, R. Right? So this one is transmission delay. Perhaps you have a question, why the access delay follow that formula? Maybe it's a different story, but the current problem that you have for that formula, so you just follow that formula. And to have the calculation according to that formula, we should have the transmission delay here, this one, delta, right? So this is transmission delay, and beta here, this is beta. 15. So this is beta. And the beta is 15. Where to find 15? This one. 15 requests per second. And follow the formula, we should have a beta multiplied delta. So this value equal to 0.9. And this is the formula. Therefore, we have the access delay 0.6. And we have the component 4 plus the access delay. So we have 4.6 for the first subproblem. All right, about this one, is it okay? So that you have 1 minute to check with your neighbors for subproblem A. So feel free to discuss about subproblem A, any possible questions or anything else. Sure, feel free. Why I try to ask international students join different groups, because I expect all of you can have the practice of English. Okay, so subproblem A, currently, I think it should be okay, right? Or maybe you should have some problems, raise your hands. No, right? Based on the fundamental formula, we should have the calculation again, this one. But this time, we have an access link with a probability of 0.5 to go through access link. So the rate will be reduced. So beta will be 15 over 2 because 0.5 multiply 15 so over 2 directly. So that's why I have multiplied 0.9 for the previous calculation, because beta, maybe I try to have the new beta. Beta prime here is 0.5 multiply beta. So it's 15 multiply 0.5. Because of that, so we have this one. And based on this one, we have the new calculation, 0.11. And so that, again, we have the formula. But this is case not hit. Right? This is a case not hit. However, we have a case 1 hit. Hit, then we have a probability a half, multiply 0, and not hit. And we have a probability a half again, multiply the corresponding access delay, the total delay 4.11. Well, so it doesn't mean you can apply the previous delay in subproblem A to have to replace the current value 0.5 multiply that value. No, you should have the new calculation because the rate to the access is halved, right? It's halved because we have the hit ratio equal to a half. And so that this is the formula to have for the calculation. And this calculation, we use the expected value or the expectation, right? So again, there you have 1 minute to check the calculation for subproblem B. Same, feel free to have further discussion. So let me check again with students in the classroom about the second subproblem. Good one. Is it okay? Okay, right? And good two? Good. Good four. Good five. And good six. All right, so this is a solution to to problem 3. And I think this one you will know how to have the calculation specifically to the second subproblem, talking about web cache. If we have a web cache, then we have 2 cases, hit or not hit. And you need to have the corresponding delay. If hit, we assume the delay is negligible. So we set it to 0. Otherwise, we should have the calculation again because the rate is different from the previous case if we don't have the cache. So you should have the recalculation. So I emphasize this one. Do not use it directly. We should have the recalculation. All right, that's all. This is the third problem of quiz number 1. And let me go to the next one. Well, so before the quiz, we have some description for the reliable data transfer. Remember that? And right now, we have the assumption. In the previous discussion, we assume perfect channel. Perfect channel, no bit errors, no packet losses. But this time, we assume we have bit errors. So, bit errors, we assume channel may flip bits. Here the same. All right, and we want to recover from errors. Recover from error, it doesn't mean, okay, I receive it and then I use forward error correction. In fact, we have one scheme called forward error correction. Oh, based on the received packet, we know how to have the error recovery directive. So it is called forward error recovery, FEC. And then the next one is ARQ. Sorry. It is called the automatic repeat request. Repeat, right? So you need to retransmit, repeat request. So we have ARQ. And right now we pass on the second one, ARQ. To have an ARQ, that says we should have a mechanism. If you think, okay, I cannot accept, so you should let me know. You cannot accept what I send to you. If so, you should resend, so you should point out which one you cannot accept, and then I should retransmit. And also, oh, okay, it's okay to accept that one. You should let me know as well. So we have this acknowledgement. And here, acknowledgement, we assume it's positive. And here, this one is negative. So we have two acknowledgements, or two types of acknowledgement. One, it is called ACK, and second one is called NEC. Well, the term acknowledgement, in fact, acknowledgement, we have maybe multiple meanings. And the meaning here, this one. Right? So this kind of acknowledgement. Therefore, we pass on ARQ, right? ARQ, so we should have the acknowledgement saying yes, acceptable, or negative acknowledgement saying not acceptable. So we have the two kinds of ACK, but we have the shorthand ACK to indicate positive acknowledgement, NAK to indicate negative acknowledgement. So we have ACK and the NEC. And based on ACK and NEC, we want to have the ARQ design, this one. And later ARQ design, we try to handle packet by packet. And that packet by packet, so we have stop and wait. Why stop and wait? Once the sender sends the packet, then you should stop and wait any possible ACK so that the sender can take the action for the next round. Sender here. You see, stop and wait. Why? Sender, wait for call from above. That says, should we have any message to be sent? If yes, then we make packet. So you can see make packet. But we have a checksum because we need to detect errors. And then UDT send. After now, I think you can accept make packet including checksum. So we have SND. So it should be correctly SND packet. All right, SND packet. And receive packet using RCV-PKT. So SND packet. And then send, we should wait. So stop and wait here. Right? We send and then wait here. In fact, we just said have a wait here, but well, I should stop. You wait there, so you stop sending. All right. So you wait there. Therefore, the sender stop sending. So that's why we have a stop and wait. And here, yes, I wait here, but I may receive the packet. So receive packet of the sender, or maybe by the sender, right? Receive packet by the sender. Then we check it. Oh, I received it, so is it ACK? All right, is it egg? So if it's egg, then everything's okay. Here, nothing to do. The notation says nothing to do. All right, the capital lambda says nothing to do. Actually, this one is capital 大写, capital lambda, and then nothing to do. So here we have the receive packet. And so this one, you receive the packet, and the packet is egg. Then, oh, okay, this one, nothing wrong. All right, so do nothing. Well, let me clear this and then go to the next one. If I receive, but it's neck, so you should send the previous packet, sorry, not previous, the current packet you made, right? So we have this case, neck, and repeat to transmit the current packet. Well, maybe let me stop here. All right, let it have 1 minute to check the current finite state machine for sender. And feel free to have a discussion with your neighbors. Maybe go to good too. Yeah. So about the current sender using the finite state machine, any possible questions, so let me know so I can repeat it. I assume no, am I right? So let me go to the discussion for receivers. Receiver here, RDT receive. So I receive the packet. So for the receiver calls, any packet to the receiver, it's treated as the RCV packet. So current one, it should be data. I receive the data, but unfortunately corrupt. So what that means, corrupt? Oh, okay, maybe later we will have the meaning for corrupt. Corrupt says I cannot access, so something wrong. Corrupt, so I sent neck. The receiver sends neck. Or otherwise not corrupt. So not corrupt, I can extract so that I can deliver. And I should let the sender know egg. Well, that's it. This is the side of the receiver. It should be easy, right? Am I right? So Fenya, okay for this one? Sure. And that says something here, but currently I skip this one to let you know this is a finite state machine for current version. Well, of course, we don't know the status of the receiver from the viewpoint of the sender. So we emphasize this again. Well, because we assume no errors, only no errors. So we have the following operations. Send, then go to the stat, wait. And then because correct, so the receiver receive it, and then we send ECK. Well, this is first case. And second case, we have the corrupted packet that says, I cannot receive it correctly. Then we have the case here. Send packet, right? Because the receiver cannot accept the packet. So we send NEC. Send NEC, and then we repeat to send the packet. You see, repeat. By this time, it's correct. Well, that's it about the final stat machine. I think you show the animation, right? So, I mean, you see the animation. So that's correct, am I right? Well, about the current scenario, sender, receiver, and so that we have the possible actions for the sender-receiver pair. It should be okay, right? Well, unfortunately, even we have the successful design for version 2.0, but we have this issue. You can guess what's the problem. It's easy. We assume no errors, but we don't have the assumption of packet losses. So, of course, it's a problem, right? So, because of the assumption no packet losses, so it is not okay. And also, we have this one as well. If packet losses, and even no packet losses, we have the current problem. Previously, why we assume ECK and NEC? ECK and NEC has no problem in the receiver side, I mean at the receiver side. In fact, not okay. So actually, we assume even we don't have packet losses, we still have the problem. The previous design, we assume ECK and NEC is okay and don't consider the corrupted ECK and NEC. It is not okay at all. So we deal with the first one first. All right, sender don't know what happened at the receiver because if we don't have the correct ECK or NEC. And how about retransmit? Someone like the receiver that the sender know, oh, it should be ECK or NEC, but the sender treat it as NEC and repeat sending the same packet again. If we do so, then we have the problem. Duplicate. Duplicate says we have the same packet to be sent. So the second one, it should be discard and keep the first one. So we have the problem of duplicate packets. Therefore, yes, we want to do so. Therefore, we gotta have duplicate handling. Sender just retransmit, right? But we should have the duplicate handling. and the sender add sequence number for each packet. And if we know where we have the duplicate packet, then we discard the duplicate packets. Well, even we don't know echo neck, but the sender just retransmit. Because just retransmit, therefore the receiver need to tell the duplicate packet or not by using the sequence number. So this time we have a sequence number. Well, if so, everything's okay. Duplicate here. All right. Same. We have the same one here. Somehow we copy the packet to have the same packet. But before we go, let us have the antenna checking first. Two minutes for you. Maybe some of you join online. So I said 2 minutes because some of you join online, and so that I can move on to the next slide. Well, so we have the new version. No losses, but we have a sequence number because we have the corrupt. Here we use a new term, garbled. You can think garbled and corrupted, they are the same. So, of course, they are different a bit. So you can check it later. Sender need to handle, sender, of course, need to accept the garble echo net, and so that the sender just repeat the transmission. And also, because the receiver need to have the chance to detect the duplicate packet. Therefore, even for the sender should prepare the sequence number. And current one, sequence number, we just prepare 0 and 1. And later, we want to know, is it okay to have 0 and 1 to serve as the sequence number? Later, we will check it for you. But we just want to do something like that. Therefore, we have this sequence number. I point out sequence number. Sequence number. Well, let it have the key terms first. Garble. And previously, we have corrupt. Maybe it's too late to let it know the meaning of corrupt, but at least we have the two meanings. Well, we let it have this one first, and then you can check it. And at least I point out sequence number 0 and sequence number 1. And so that we have two cases, 1 and 0. And in fact, 0 the same as the previous one, 1 similar to the previous one, but we have sequence number 0 and sequence number 1. All right, let me pause here, and of course you can check it later. Oh, sorry. You can check it later, but for student online, maybe you cannot check it. You can check the slides. All right, so up to now, it's okay. If it is okay, take a rest, and then we can continue.